Let's start. So, in this week, in the week 6, some questions for Z transform were discussed, and Fourier series was introduced and discussed a bit in detail. So, the first thing that was covered was inverse Z transform. So, if we have a discrete time signal x of n, and if its Z transform is x of z, then we can recover back this x of n from x of z using the inverse Z transform, which is given by the formula 1 upon 2 pi j contour integral over gamma xz z to the power n minus 1 dz, and this gamma is basically a region. It is basically a closed contour which encloses all the poles of this xz into z power minus 1 in counterclockwise sense. Now using this equation and solving this integral every time becomes a bit difficult. So for that we make use of the general or the standard formulas or standard Z transforms or standard signals that we know, and make use of them to find the inverse Z transform. Another method to find the inverse Z transform was this general inversion method, where this x of n, this inverse Z transform, this integral, basically reduces to summation of I equal to 1 to p residue or of this z tending at pi, and this residue is of x of z into z to the power n minus 1. And the definitions for this residue for simple pole and pole with multiplicity was also discussed. We'll look at one simple example of this. We'll solve the same question which we had solved using power series method and another this standard method that we are generally using. After that, this Fourier series for continuous time signals was introduced. So what is the role of this Fourier series? So basically this Fourier representation takes us from time domain to frequency domain and allows us to visualize many things which can't be visualized in time domain. So basically this Fourier series is for periodic signals. This is defined for periodic signals. And if a signal is periodic with period t, that is if x of t is periodic with, let's say, period t naught, and this is the smallest period, smallest t naught, after which that particular signal repeats, then this is known as the fundamental period. Then the fundamental angular frequency omega naught is simply 2 pi by t naught. This is angular frequency, and all the integer multiples of this omega naught, that is k times omega naught, are basically harmonics of this fundamental frequency. After that, the complex Fourier series was discussed. So what it says is any periodic signal, let's say x of t, can be written as summation with some coefficients, or let's say linear combination of some complex exponentials, where this x of t is periodic with period t naught and fundamental frequency omega naught. So this x of t is periodic with omega naught angular frequency, and this x of t is simply represented as a linear combination of these complex exponential with frequency omega naught t. And this is known as the complex Fourier series. Further, along with this complex Fourier series, we also have the trigonometric Fourier series representation, which is given as a naught by 2 plus summation k running from 1 to infinity ak cos of k times omega naught t plus bk sin of k times omega naught t. And there is a good relationship between these a naught ak and bk's. So basically this a naught by 2 is equal to c naught. Then your ak is twice real part of ck and bk is minus 2 times imaginary part of ck. Furthermore, in order to obtain this ck, we have inverse Fourier series formula, and it is given as, so this ck can be obtained as ck is equal to 1 upon t naught integration over a period interval x of t into e power minus jk omega naught t dt. And this is how we obtain this ck, that is the Fourier series coefficients. The ck are known as the Fourier series coefficients. Now there are several conditions for existence of Fourier series, and these conditions are known as Dirichlet's conditions. And these conditions say that if a signal is absolutely integrable over a period, it has a Fourier transform. Or specifically, it says that if a signal has Fourier transform, then it is absolutely integrable over a period. It has finite number of maxima and minima over a period, and finite number of finite discontinuities it should have. And next thing that was discussed was power of periodic signals. So it said that the power of periodic signal is basically given as 1 upon t naught integration over a period mod of x of t square dt, and this is exactly equal to summation k running from minus infinity to infinity magnitude of this ck square. So these are the concepts that were covered in the previous in the week 6. Now let us start looking at some of the questions. If there are any questions till this point, please let me know.
Hello, good evening, ma'am.
Yeah,
I'm Adarsh. I'm like, I have not yet studied this topic, but if I have any doubts, can I ask in next meet, like
yeah, you
tomorrow's meet?
can.
Like,
You can.
okay, ma'am. Thank you.
Yeah.
Okay, ma'am. Thank you.
You may also post it in the portal of NPTEL. So we will also be available on that portal also. You have a group, right? You can put your questions in that also. If you if you don't want to wait till the next meet, that will also help you out. We'll try to answer them.
Okay, ma'am. Okay, ma'am. Thank you.
Yeah.
Madam, actually there is a delay. The current week assignment is actually 7. So maybe whatever you are sharing now, that assignment was already over. Help. So yeah. So I think I have. This is one problem. Okay. So yeah. So if you can skip or shift to week 7, that will.
Okay. So this week I'll just go with whatever content I have. Okay. In the previous week's tutorial, we had solved this question using the other two methods, that is the power series based method and partial fractions method. And yeah. So now in this question, we'll use a general inversion method to solve the same question. So now let me just write this in more simpler form. That is, I can just write it as z square upon z square minus 1.5 z plus 0.5, which is equal to z square into z minus 1 into z minus 0.5. Now let us consider this h of z into z to the power n minus 1. So this is equal to z to the power n plus 1 upon z minus 1 into z minus 0.5. Now I need to find the residue of these. So if I consider residue of this at pole 1, then since it is a simple pole, it is given as limit z tending to 1 and this factor, that is z to the power n plus 1 upon z minus 1 into z minus 0.5 multiplied by z minus 1. This gets cancelled and I can just simply substitute 1 here. So it is 1 to the power n plus 1 upon 1 minus 0.5, that is 0.5. So this comes out to be 2 to the power 2 into 1 to the power n plus 1, and this we are basically finding for n greater than or equal to 0 because we are having causal system. Next thing that we'll find is residue for my pole as 0.5. So this is equal to limit z tending to 0.5 z power n plus 1 upon z minus 1 into z minus 0.5 into z minus 0.5. This gets cancelled and this comes out to be 0.5 to the power n plus 1 upon minus 0.5. This is equal to minus 2 into 1 by 2 into 0.5 to the power n, and this is equal to minus 1 by 2 power n, and therefore my h of n will be summation of this and this. So my h of n will be 2 minus 1 by 2 to the power n, and this is obtained for n greater than or equal to 0, hence u of n. And if we observe carefully and if you look at your previous week's notes, this is exactly the same equation that we have obtained in the previous lecture. Any questions for this?
On the other method, just I forgot, can briefly mention other method you said power series.
There were two methods that we had done. One was we had represented it, this h of z, we have considered h of z by z equal to c1 upon z minus 1 plus c2 upon z minus
Oh,
0.5,
yeah,
and
partial.
found the value of c1 and c2 and obtained this equation. And the second method that we had considered was we had considered this equation as it is 1 and 1 minus 1.5 z to the power minus 1.
Okay, I remember.
Yeah. So both of these equations, both of these methods gave the same answer. Now we are just using this general inversion method and we observe that we are getting the same answer, just for a check. Okay. Now let us look at some questions which are based on Fourier series. Like we'll solve all the questions which are coming up for the Fourier series. So the first question that we have is we have been given this signal xt, and this is my unit impulse, and this L is varying from minus infinity to infinity. So let me just sketch this signal. So this is my time axis, this is 0, and I'll be plotting x of t here. So now if my L is equal to 0, then I have an impulse at t equal to 0, Then if my L is equal to 1, then I'll have an impulse at 1, or let's say t, not 1. If my L is equal to 1, I'll have an impulse at t. This is t. Similarly, I'll have an impulse at 2, and so on. Also, I'll have an impulse at minus t, at minus 2t, and so on. So this is basically a train of impulses. And this x of t is periodic with period t. Therefore, the angular frequency omega naught is simply 2 pi by t. Now we need to find the Fourier series coefficient Ck, which is equal to 1 by t naught, or 1 by t integral over some period. So let us consider this period, this range, this one, that is from minus t by 2 to t by 2. So if I consider the integral from minus t by 2 to t by 2, in this the x of t is taking value as delta t multiplied by e power minus j k omega naught t dt. Now this is a unit impulse, and we know the shifting property of unit impulse, that is, if I have x of t, or let's say, in order to avoid confusion, let me use some other function. Let's say I have phi t into del of t, then this becomes phi of 0 into del t. Here my phi of t is this factor. So now I can simply replace this t by 0. So what I have is 1 by t integral from minus t by 2 to t by 2 delta t e power minus j k omega naught 0 dt. This factor here is equal to 1, so I can just simply ignore it.
Madam, just 1 minute.
Hmm.
Here, when you are calculating Fourier coefficient Ck,
Hmm.
the xt is a full series, right? Sigma L
Yes.
equal to infinity, but you have substituted only delta t.
Yes, because while finding Fourier series, you integrate it over a interval of time period. Your integration is over one time period interval.
No,
So
no, that I understand. Minus t by 2 plus t by 2, I understand.
yes,
Instead of xt, you have just put delta t.
yes, because if I observe this interval from minus t by 2 to t by 2, this interval here,
Yes.
I am considering this interval now. So in
Okay.
this interval, my x of t is just delta t. So
Okay.
this is delta t.
Okay. 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 Remaining becomes
Yeah, this is
the.
delta t minus capital T. This is delta t minus 2t. So remaining are not considered. They are not a part of this interval.
Okay. Okay, madam. Got it.
Yeah. Okay, so this integration becomes 1 by t integral from minus t by 2 to t by 2 delta t dt. An integration of an impulse over an interval when the impulse is included in that interval is equal to 1. So this is simply 1 by t. So if I have a unit impulse, its Fourier series coefficients take value as 1 by t for all k. So if I just plot it, this is the k axis, this is 0, then my Fourier series will be simply 1 by t, 1 by t, 1 by t, and so on. Similarly for this also. This will take the magnitude as 1 by t, this is 0, this is 1, 0, 1, 2, -1, -2, and so on. So this is how the Fourier series coefficients will look for an impulse. Any questions? This train of impulse is an important thing. Like it is used a lot when we go for sampling. So it's better to have a good idea about its Fourier series, its Fourier transform.
Madam, here impulse means we can interpret as amplitude, right?
Where?
In the Fourier series graph you have written K,
Yes.
that graph we can interpret as magnitude or amplitude.
Yes, this Ck, if you consider, it is 1 by t. So if I consider magnitude of Ck, it is 1 by t, and if I consider angle of Ck, it is 0.
Yes.
So this is basically your magnitude of Ck and the angle is 0.
Yeah.
Okay. Now let us look at two other important functions or signals that are sine and cos. And one approach is use this integration equation and find the Fourier series. So I won't do that. I'll use this complex exponential based representation of sine. So we know that if my x of t is sine omega naught t, then I can write it as e power j omega naught t minus e power minus j omega naught t upon 2j. Now let us look at this equation, that is x of t, which can be represented or written as summation of the complex exponentials as ck e power j k omega naught t. Now if I compare this and this, so here we know that this is a sinusoid with frequency omega naught. So this is a sine with frequency or angular frequency or fundamental angular frequency as omega naught. So if we consider this, if we look at this I can write as 1 by 2j e power j 1 omega naught t minus 1 by 2j into e power j into minus 1 into omega naught t. And if I compare this and this, I can say that this factor here is simply ck when my k is equal to 1. So this is simply c of 1, and this factor here is c of minus 1. So my c1 is equal to 1 by 2j and my c of minus 1 equal to minus 1 by 2j, and ck is equal to 0 for all k which are not equal to minus 1 and 1. Is this okay? Okay. Similarly, I can do the same thing for this cos, that is I have xt is equal to cos of omega naught t, and this I can write as 1 by 2j, sorry, e power j omega naught t plus e power minus j omega naught t upon 2. This is equal to 1 by 2 into e power j omega naught 1t plus 1 by 2 into e power j omega naught minus 1 into t. So in the same way, if I compare it with this equation, then this 1 by 2 is my c1 and this 1 by 2 is my c of minus 1. So I can write as ck is equal to 1 by 2 if k is 1 or minus 1, and it is equal to 0 otherwise. Any doubts in this question? Okay. Let us look at the next question now. In the similar way, we can use whenever we have sine and cos, it's better to go for this representation because using integrals really become a lot of calculation. So we can just make use of the complex exponential ways representation of sinusoids and go ahead with it. So again, when I have this x of t, I can write it as sine of omega naught t plus the sine square omega naught t can be written as 1 minus cos of 2 omega naught t by 2. Now this sine here I can write as 1 by 2 e power j omega naught t plus 1 by 2 e power minus j k omega naught t. Then we have this 1 by 2 as it is, and minus 1 by 2, and this cos can be written as, sorry, this is 2j, 2j. This is a sine, so it will be 1 by 2j. And this cos can be written as 1 by 2 into e power j k j2 omega naught t plus 1 by 2 into e power j2 omega naught t. So this I can write as 1 by 2j e power j omega naught t minus 1 by 2j e power minus j omega naught t plus 1 by 2 minus 1 by 4 e power j2 omega naught t minus 1 by 4 into e power j into minus 2 omega naught t. Now here, if by observation we can see that it has a fundamental frequency as omega naught, because this is the smallest frequency, and the LCM, I'm sorry, the HCF of these two is anyway omega naught. So again, if I compare it with this equation here, I can see that this is my C1. This entire thing is C of minus 1. Now this is C0 because C0 into e power J0 omega naught 0 t is equal to C0 into 1. So there is no complex exponential attached with it. So this is the DC component or C0. Then this factor here is simply C of 2, and this factor here is C of minus 2. Therefore, the Fourier series coefficients that we have obtained here is C1 is equal to 1 by 2j, C2 or C of minus 1 is equal to minus 1 by 2j, C0 is equal to 1 by 2, C2 is equal to minus 1 by 4 is equal to C of minus 2, and otherwise it is 0. Any doubts in this part? Okay, if not, then let us move on to the next question. So in this question, we are given a signal which is something like this. So basically it is a signal, it is a rectangular ball string which goes something like this, and okay, it is extending from minus infinity to infinity. So this is my x of t, and we need to find the Fourier series coefficients for this. So we know that the Fourier series coefficients are given as ck is equal to 1 by t integral over a period t. We can observe here the fundamental period of this signal is t, and from this we can say that the fundamental angular frequency is simply 2 pi by t. So it is integral over a period xt into e power minus j k omega naught t dt. This I can write as 1 by t integral. So if I just consider this interval from 0 to t, I'll just consider this interval. So if I consider this interval, then for 0 to t by 2, this x of t takes the value as this x of t is equal to 1, and if I consider this interval from minus t by 2 to 0, that is minus t by 2 to t, then this x of t takes a value as minus 1. So I can split this integral from 0 to t by 2 and t by 2 to t. So I can write it as 0 to t by 2 x of
Madam, 0 to t by 2 and t by 2 to t, no? Not minus t by 2.
sorry, t by 2 to t. Yeah. From t by 2 to t, it takes the value as minus 1. One into e power minus j k omega naught t dt plus 1 by t integral from t by 2 to capital T minus 1 into e power minus j k omega naught t dt. So let us take the first, let us try to solve this. So we have ck is equal to 1 by t, and this e power minus j k omega naught t integrated with respect to t gives as minus j k omega naught t upon minus j k omega naught from 0 to t by 2, and this is minus 1 by t. I am just taking this minus sign outside, and the same thing repeated as e power minus j k omega naught t upon minus j k omega naught, and now this is integrated from t by 2 to t. Now this omega naught is 2 pi by t, so I can replace that in this equation. Also, if I consider, okay, I'll just replace it in the equation. So the ck is equal to 1 by t, then it is e power minus j k 2 pi by t t upon minus j k 2 pi by t minus, this is from 0 to t by 2, 1 by t e power minus j k omega naught, where this omega naught is 2 pi by t upon minus j k 2 pi by t from t by 2 to t. So if I observe here, this t gets cancelled, this t also gets cancelled, and I can write this now as, so the ck is equal to e power minus j k 2 pi by t e power minus j k 2 pi by t into t upon minus j k 2 pi, and this is from 0 to t by 2, minus e power minus j k 2 pi by t into t upon minus j k 2 pi from t by 2 to t. Now this I can write as 1 minus e power minus j k, this t by 2 I can substitute here, so it becomes j k pi upon j k 2 pi minus, then this becomes, I'll substitute this t here, so, or I'll just take this sign outside, this becomes plus, so I substitute this t here, so this becomes e power minus j k 2 pi, this t and this t gets cancelled, minus e power minus j k pi upon j k 2 pi. Now we have these terms here, e power minus j k pi and e power minus j k pi. Now let us consider these, e power minus j k pi. So this is equal to cos of minus k pi, which is equal to cos k pi, plus, or let's say minus j times sine k pi. Now this goes to 0 because integer multiple of pi, if I take sine of integer multiple of pi, it goes to 0, so this is 0, and this k pi, this takes the value as 1 if k is even, and this takes a value as minus 1 if my k is odd. So I can write it as minus 1 to the power k. So if my k is odd like 1, 3, 5, then this will be minus 1, and if it is even, then I can write it as then it is minus 1 to the power 2, so it is 1. So therefore I can replace these two terms by minus 1 to the power k. Now let us look at this factor here, that is e power, this factor, e power minus j k 2 pi. So this I can write as cos of k 2 pi minus j times sine of k 2 pi. Now again this is integer multiple of 2 pi, this goes to 0, and this factor here is even integer of pi. This 2 times k for all the integer values of k will be an even number, and therefore this is even integer of pi, and therefore using this logic mentioned here, this cos of 2 pi k will lead to 1. So this is equal to 1. Therefore I can substitute these two values here. So we have ck is equal to 1 minus minus 1 to the power k upon j 2 pi k plus 1 minus minus 1 to the power k upon j 2 pi k, and this is equal to 1 minus minus 1 to the power k upon j 2 pi k. Now notice here, when I am finding this integration, this first term itself, this is valid only when my k is not equal to 0. This I am finding only when my k is not equal to 0, otherwise this term has no meaning. So we will now explicitly find what happens when my k is equal to 0. So we'll find when my k is equal to 0. So we'll go back to the initial equation that we had considered, that was this integration over a period x of t into e power minus j k omega naught t dt. This we had separated over two parts, that was from 0 to t by 2 where x of t was 1 into e power minus j k omega naught t dt, and minus integration from minus t by 2 to t e power minus j k omega naught t dt. Now here we will substitute k is equal to 0, then we have c0 is equal to 0 to t by 2. Here we will substitute k as 0, so this goes to 1 dt minus integration from t by 2 to t e power minus j k omega naught t. So this factor k is equal to 0, so this reduces to 1 dt. And now this first integral is t from 0 to t by 2 minus it is t from t by 2 to capital T. This reduces to 2. Yes,
Madam, in the above CK equation,
this one.
uh, 0 to t by 2 e to the power of minus jk omega naught t dt, you said minus.
Yeah, because from my signal was like this, right?
Oh, okay, okay, okay,
Yeah,
okay,
so
okay,
from
okay.
till t by 2.
Every bit minus. Okay, okay.
Yeah, minus t by 2. So this is equal to 0. So my C naught is equal to 0 and my Ck comes out to be 1 minus minus 1 to the power k upon j times k pi. Any questions in this part? Okay. Let us look at this signal here. Now this is another signal which looks a bit similar to the previous one. So if I look at the previous signal here, the previous question signal, it was something like this.
Okay. Only there is no negative component. Okay.
Okay, now if I shift this signal by 1 unit upwards, then I'll get this signal. So if this is my x tilde t, then and this is my xt, then my xt is equal to 1 plus x tilde t. Is it okay? Now we will find the Fourier series coefficients of this xt and try to figure out if these two have some relation or not. So you have any questions?
Yeah. Okay. Okay. So that x tilde t, sorry, xt is nothing but shifted up.
Yes, I am just shifting this x tilde t upwards by 1 unit.
Okay. So everything moves to the positive
Yes.
x. Okay. Okay. Okay.
Okay. Now let us try to find the Fourier series coefficients of this xt. We know what are the Fourier series coefficients of x tilde t. We have obtained them here. And we'll try to see if there is some sort of relation between this xt and x tilde t's Fourier series coefficient. So let's start. Now again here the fundamental angular frequency is 2 pi by t because the period is same. And this xt, if I consider it from 0 to t by 2, it is equal to 2. So it is 2 if t belongs to 0 to t by 2, and it is equal to 0 if t belongs to t by 2 to t. So we'll again consider this interval, this one. So we have it as 1 by t integral from 0 to t xt e power minus j k omega naught t dt, which is equal to 1 by t integral from 0 to t by 2. In this range it is 2 e power minus j k omega naught t dt, and the second integral from t by 2 to t goes to 0 because in that region this x of t takes value as 0. So now this is equal to 2 by t integral from 0 to t by 2 e power minus j k omega naught t dt. So this I can write as 2 by t integral from, let's say I'll solve this integral. This exponential gives me a value as e power minus j k omega naught t upon minus j k omega naught, and this is from 0 to t by 2. Again this is valid only when my k is not equal to 0, because this k is coming at the denominator. Now let us substitute the value of this omega naught as 2 pi by t. So this is equal to 2 pi by t, 2 by t into e power minus j k 2 pi by t upon minus j k 2 pi by t from 0 to t by 2. This t and this t gets cancelled. Similarly, this 2 and this 2 gets cancelled. This is equal to e power minus j k 2 pi by t upon minus j k pi from 0 to t by 2. Now if I substitute it, this comes out to be 1 minus e power minus j k pi upon j k pi, and again we have seen that e power minus j k pi is simply 1 minus to the power k upon j k pi. Now let us consider the case when my k is equal to 0. So in that situation, this integral here reduces to c0 equal to 2 by t, integral from 0 to t by 2 e power minus j0 omega naught t with dt, which, and this reduces to 1. So this is simply 2 by t from 0 to capital T by 2, which comes out to be 2 by t into t by 2, which is equal to 1. So what we have obtained is c0 is equal to 1 and ck is equal to 1 minus 1 to the power k upon jk pi. Now look at this equation, this Fourier series coefficients. These are the Fourier series coefficients for the case of x tilde k, x tilde t, and these are the Fourier series coefficients for xt. The only difference is here c0 was 0 and here c0 was 1. So when I am shifting it by 1 unit upwards, I am simply giving it a DC shift. A DC shift by 1 unit, and the DC shift is always reflected in the DC component of Fourier series, that is C0t. So if I am shifting this by 1 unit upwards or some unit downwards, the only change is in its average value, and the average value of the signal is captured in the DC coefficient, that is C0t. So if I am having a signal given as x tilde t, and someone gives me a signal xt which is a shifted upward or shifted downward version, I can find the Fourier series coefficients of it, and I know the Fourier series coefficients of this x tilde t, then I can simply make the changes in its DC components, that is take c naught equal to 1. Is it okay?
Yeah, madam, suppose we shift downwards x tilde t,
Hmm.
then it will be same. The whole thing shift downwards, negative.
If the whole thing shifts downwards, negative, then from minus t by 2 to t by 2, it will be 0. Sorry, if I shift this from like downwards, like this, right? If I'm having it something like this,
Yes, yes.
Okay, so this is 0, this is t by 2, 0, t, and so on, and this will be minus 2. Now I am shifting this x tilde t downwards by minus 1. So this minus 1, for this signal, my c naught will be equal to minus 1, and ck for k naught equal to 0 will again be this factor.
Okay. Okay, okay. Okay, okay, okay.
You
C
want
not
me to
big.
solve it once?
Yeah, yeah. Okay, okay. I understand.
Okay, yeah. So this is actually when you're shifting up or down, you are just adding some DC level to that signal. You are adding a DC component.
Yes.
Like if you compare these two signals, these three signals, this xt, x tilde t, this xt, and let's say this is x1 of t, the only difference in these three is the average value over a period.
Okay, okay.
This
Next tilde t case it is 0. So
yes,
shifting up it gives +1 and shifting down it becomes -1.
yes,
Okay, okay.
yes. Okay. Now let us look at the next question, and this is we need to find the Fourier series coefficients of the signal xt, which is given something like this, and this is t. Or let's say, let us take a special case when my t, this capital T, is equal to 1. So let's say this is 1 to make the calculations a little, or let's say it is 2, not 1, this is 2, that is t equal to 2. Then my angular frequency omega naught is equal to 2 pi by t, which is equal to pi. 2 pi by 2, which is equal to pi. This is t by 2, which is equal to 1. Then if I consider from -1 to 1 this interval here, this is one period interval, and this interval is simply this interval. In this interval, my xt is simply equal to t. So now let us try to find the Fourier series coefficients of this. So we have ck is equal to 1 by t integral from minus infinity, integral over a period from minus t by 2 to t by 2. So to be specific, it will be from -1 to 1, and my t is equal to 2, so I can replace this by 1 by 2, that is t, e power, and x of t in this region is 1, then e power minus j k, omega naught is pi t dt. Now this I can write as minus t into e power minus j k pi t minus e power minus j k pi t upon, and I have a minus j k pi whole square from -1 to 1. So this comes out to be 1 by 2. I can substitute this here, so it is -1 into e power minus j k pi upon j k pi plus e power j k pi, this is minus, this is plus times -1, this is minus e power j k pi minus, we can write this as e power minus j k pi minus e power minus j plus j k pi upon j k pi whole square. Now if I consider this factor here, this is equal to minus 1 to the power k. This is also equal to minus 1 to the power k. So this entire term goes down to 0, and this I can write as minus 1 by 2 into minus 2 times minus 1 to the power k upon jk pi. This is equal to this gets cancelled, and minus 1 by j I can write as j times minus 1 to the power k upon k pi. And again, when I'm solving this integral, the basic assumption is my k is not equal to 0. So now if my k is equal to 0, then in that case this integral this term goes to 1. So my c0 is simply 1 by 2 integral from minus 1 to 1 t dt. Now this t is an odd function, and therefore this will go to 0. So the c0 is equal to 0. Any doubts in this part?
Madam, most of the examples we see in Fourier series involve either the square pulses or triangular pulses like this, right? Yeah, because I see in almost all textbooks they cover square pulse and triangle pulse.
Yes.
Okay, but yeah.
These are some of the standard examples and some simple signals which we may like sort of remember or have some idea how its Fourier series will look. Like actually this gives something more insightful. Like if you observe this equation here, this signal is looking something like this, right? Like it is having one fundamental frequency and so on, but actually this square pulse is constructed to using multiple complex exponentials or multiple sinusoids which are non-zero, which have non-zero amplitude only at some particular values of k. That is, if I have my k as even, then this ck will go to 0. If my k is odd, then it will be non-zero. So basically if we draw it now, it looks something like this. This is 0, at 0 it is 0, then at 1 it will have some magnitude, then again go to 0, then something here, then 0. So this is 1, 2, 3, 4, 5 and so on. So this is a simple signal that we may be able to visualize, but it has many frequencies that are contained in this. Now by just observing this sequence in time domain, the signal in time domain, we can't get this interpretation. So basically going from here to here, we are getting some additional information like what all harmonics are non-zero, what all kind of frequencies are present. So this kind of analysis helps a lot when we need to design systems. Now that this may not be clear in Fourier series, but once the Fourier transform is covered, at that time we'll see that okay, this representation, this visualization helps a lot in designing of filters and other stuff. So that's why this analysis helps.
Okay.
Yeah. And many times this triangular and this rectangular pulse are related things. And when we'll see in Fourier transform, then differentiation and integration properties play a role. And in that time, we'll see the properties, how these things get related and how it helps in solving the questions. Okay. Now let us look at this question. So here I have been given this xt as summation over L. This L is running from minus infinity to infinity, x1 of t minus L. And this x1 of t is given something like this, and this is non-zero only for the interval from 0 to t, and it takes the value as e power minus t. So let us first draw this x1 of t. This is my x1 of t. This is 1. So the signal starts from 1 here, goes till 1, and then is 0 otherwise. And now this signal, this x1 of t, is repeated after lth instant, after every lth instant, from minus infinity to infinity. So this xt is basically something like this. This is x1 of t till 1. Then this is x1 of, this is 1. This is x1 of t minus 1 till 2. Then it is x1 of t minus 3, t minus 2, and so on. Similarly, this is x1 of, this is, if I be specific, this is x1 of t plus 1, and this is x1 of t, and this is x1 of t minus 1, and this continues. So this is the xt, and if we observe that this xt is periodic with period t equal to 1, and its angular frequency omega naught is 2 pi by 1, which is equal to 2 pi. Yeah.
Okay, this looks interesting. That means we can express periodic functions using that notation. Xt is equal to sigma of L x1 of t minus L,
Yes.
right?
Yes.
It could be any x1, any
Any
x1.
x1.
Okay.
If I consider this x1, like here I am taking the period as 1. So in general, if this is not having a period 1 but having a period t, I can represent it as xt equal to summation L running from minus infinity to infinity x1 of t minus lt, where this x1 of t will be non-zero only for 0 to capital T duration.
Okay, okay. So basically, what x1 of t minus L indicates is it is shifted versions of x1t to the right,
Yes.
uh, L to L, like that, right?
Yes. Yes.
Okay.
If my L is positive, then it is towards right. If my L is negative, then it is towards left.
Yes.
Yes. Okay. Now we need to find the Fourier series coefficients of this xt. And again, if we look at this signal here, we'll just consider this interval from 0 to 1. And we have ck is equal to 1 by t, where my t is 1. So I can write it as 1 by 1 integral from 0 to 1 xt in this interval is simply e power minus t into e power minus j k omega naught t dt. So this is equal to 1 upon 0 to 1 e power minus t. I can write it as e power minus t, I can take out common, 1 plus j k omega naught dt. Now this I can write as e power minus t 1 plus j k omega naught upon minus 1 plus jk omega naught, and this is running from 0 to 1. Now after substituting it, this comes out to be 1 minus e power minus 1 plus jk omega naught whole divided by 1 plus jk omega naught. And now this omega naught takes the value of 2 pi, so I can simply substitute it. So I can write it as 1 minus e power minus 1 plus jk 2 pi upon 1 plus jk 2 pi. This I can write as 1 minus e power minus 1 into e power minus jk 2 pi upon 1 plus jk 2 pi. Now this factor here, this is equal to 1 as we have seen it previously. So this e power minus jk 2 pi is equal to cos of k2 pi minus j times sine k2 pi. This goes to 0 and this cos of k2 pi takes value as 1, and therefore this simplifies to 1 minus e power minus 1 upon 1 plus j times k2 pi. Any doubts at this point?
Uh, yes, maybe, madam, in this session, if you can explain Fourier series versus Fourier transform versus Z transform one before we end up the session,
Yes,
will be
sure,
nice.
sure. I have two more questions to do, and then
Okay, good.
I'll discuss that. Maybe that will help you a bit.
Okay.
Okay. Now the next question is a bit simple one, but it is on existence of Fourier series. So we have Dirichlet's conditions, which says that if the following three conditions are not satisfied, then the signal won't be having a Fourier transform. So the three conditions were, first thing was the signal should be absolutely integrable for over a period. Then the second thing was it should have a finite number of maximas and minimas. And the third condition was finite number of finite discontinuities. So these three are known as Dirichlet's conditions. Okay, so we need to find whether the following signals have a Fourier series or not, it exists or not. So the first signal is this xt, which is equal to cos of 1 by t. Now by looking at this, we are not able to figure out what exactly is happening, so we'll try to draw this. This is with respect to t, and this is for 0 to t, and then it repeats and so on. So now if my t is very small, then this cos of omega naught, or let's say this I write it as omega, if where my omega is 1 by t, if this t is very small, my omega is very large, which means that I'll have a very fast oscillations when it is near to it, and when it is near to 0, its frequency is as good as infinite. At 0 its frequency is infinite, that is I'm having infinite number of oscillations at t equal to 0, which will be something like I have lot of oscillations here, which will then reduce a little bit and will go something like this Again in the next interval it will be similar, it will have lot of oscillations here and then it will get reduced, something like this. Again in the third interval it will have lot of oscillations here and then it will be something like this. So if we focus on this part which is very close to 0 or very or at the beginning of an interval, or let us say we just focus on the first interval, that is at 0 to t, when when t is approximately equal to 0, this omega tends to infinity, which means that we have infinite oscillations. Now this is a cos function. This cos has a minima as 1, that it takes a minimum value as -1 and maximum value as 1. But if I am having infinite oscillations, this -1 and 1 are obtained infinite number of times. That is, I am having an infinite number of maximas and minimas. So when this is happening, I am having infinite number of maximas and minimas, which means that this second condition, second Dirichlet's condition, is violated. And therefore, this is the Fourier transform for this won't exist. Fourier series, I'm sorry. No Fourier series. The next part of this is x of t is equal to 1 by t for t belonging to 0 to t, and it repeats. So it is basically periodic with period t. So in 0 to t interval, this xt takes the value of 1 by t. Now let us check its absolute integrability. So if I check integral of magnitude of mod xt dt over a period, not from minus infinity to infinity, from 0 to capital T, then this is equal to integral from 0 to t 1 by t dt. Now if I look at this 1 by t actually gives me log t from 0 to capital T. This is equal to log t minus log 0. This factor is minus of minus infinity, that is this entire thing tends to infinite, which means that this xt is not absolutely integrable. This is not absolutely integrable, and hence the Fourier series does not exist. Any doubts at this point? Okay, this is the last question that I had planned to cover, and after that we'll look at the Fourier series and Fourier transform and Z transform relation, and I'll also give relation with Laplace transform as well. Now this is the last question that we are taking, and this will basically validate the power of a periodic signal thing that was discussed here, that was seen here. We'll try to validate this. This is actually a very helpful equation in many scenarios, when especially when the signal is very complicated in time domain, but it has a very good or simple representation in frequency domain. So in that situation this equation actually helps a lot. So we have given a signal xt something like this, and we need to find its power. So power of a periodic signal is simply 1 by t naught integral from minus, let's say from 0 to t naught, two times sine omega naught t plus 5 times cos of 2 omega naught t whole square dt. So this I can separate out as I'll keep this 1 by t naught, where this t naught is the fundamental period and this omega naught is 2 pi by t naught. Okay, and now this I can write as integral from 0 to t naught. This is 4 sine square omega naught t plus 25 cos square 2 omega naught t plus 20 sine omega naught t cos of omega naught t dt. Now this sine square omega naught t I can write as 1 by t naught.
Madam, cos of 2 omega naught t, right?
Yeah, cos of 2 omega naught t. This I can write as 1 minus cos of 2 omega naught t by 2. This part cos of 2 cos square 2 omega naught t I can write as 1 plus cos of 4 omega naught t plus this part, this I can write as, or I can make this as 10 into 2. So this 2 times sine omega naught t and cos 2 omega naught t, I can use the formula of sine a plus b plus sine of a minus b. So I can write this as 10 times sine of omega naught plus 2 times omega naught, that is 3 omega naught t plus sine of omega naught minus 2 omega naught, that is sine of minus omega naught. So I can write it as minus of sine of omega naught t dt. Now I can separate out these integrals, that is 1 by t naught. I can write this 4 by 2 outside, integral from 0 to t naught 1 dt minus 1 by 2 integral from 0 to t naught cos of 2 times omega naught t dt plus 25 by 2 integral from 0 to t naught 1 dt plus 25 by 2. So we have 4 here as well. Integral from 0 to t naught cos of 4 omega naught t dt plus 10 times integral 0 to t naught sine of 3 omega naught t dt minus 10 times 0 to t naught sine of omega naught t dt. Now this t naught is basically 2 pi by omega, or this omega naught is basically 2 pi by t naught. So whenever I am having integer multiple of omega naught, or if I integrate this sign over an integer multiple of t naught, then actually this reduces to 0. So this part and this, all the signs go to 0, and the only terms remaining are this one and this one. So if I consider this and this, what I get is, so what I basically have is 1 by t naught integral from 0 to t naught 4 by 2 dt plus 1 by t naught integral from 0 to t naught 25 by 2 dt, which is equal to 4 by 2 t naught t from 0 to t naught plus 25 by 2 t naught t from 0 to t naught, and this comes out to be 4 by 2 plus 25 by 2. This is equal to 29 by 2. So this is what we have obtained. Now let us now try to see whether that property holds or not. So the signal that we have is xt is equal to 2 times sine omega naught t plus 5 times cos of 2 omega naught t. Now this I can write as 2 times 1 by 2j e power j omega naught t minus 1 by 2j e power minus j omega naught t, and this 5 cos 2 omega naught t I can write as 5 times 1 by 2 e power j 2 omega naught t plus 1 by 2 e power minus j 2 omega naught t. Now this I can separate as 1 by j plus 1 by j 1 by j into e power j omega naught t minus 1 by j into e power minus j omega naught t. This I can write as 5 by 2 e power j 2 omega naught t plus 5 by 2 into e power minus j 2 omega naught t. So if I compare it with the x of t equal to summation of complex exponential equation, then my c1 is 1 by j, my c2 is this, that is 5 by 2, then my c of minus 1 is equal to minus 1 by j, and my c of minus 2 is again 5 by 2, and ck is equal to 0 otherwise. So now let us consider this, that is summation k running from minus infinity to infinity, norm of mod of ck square. So basically it is mod c1 square plus mod c2 square plus mod c of minus 1 square plus mod of c of minus 2 square. So this is equal to 1, that is 1 by j, absolute value is 1. Then this is also equal to 1. This comes out to be 5 by 2 square, that is equal to 25 by 4. This also comes out to be 25 by 4. So this is basically equal to 2 plus 25 by 2, which is equal to 4 plus 25 by 2, which is equal to 29 by 2, which is same as what we have obtained here. So what we observe is, if I have a simple representation, this representation in the frequency domain, this Fourier series domain, was very simple. Like I just had few coefficients, like hardly 4 coefficients I had, which I just had to take its absolute value and add up. Whereas in the time domain, I had to consider these long integrals and then find the power. So this calculation becomes simpler if the frequency domain representation is easier. Any doubts in this question? Okay, so sir, you wanted the discussion which is related to the transform or relation between your Fourier transform, Laplace transform,
And and DTFT and Z transform.
okay, okay, fine.
I think all are related.
Yes, Z transform, Fourier transform are related.
Yes, yes.
Yes.
So, for
And
example,
Laplace is also related.
yeah, Fourier transform and Laplace transform are related.
Yes.
The DTFT and Z transform are related.
Yes. Yes. Exactly. So let us first consider the continuous time case. So in this case, the transforms that are needed is the first one is Z transform, and the second one is your DTFT, that is discrete time Fourier transform. So if I consider this Z transform, this x of z is given as summation n running from minus infinity to infinity x of n z to the power minus n, and this DTFT is given as x of omega is equal to summation n running from minus infinity to infinity x of n into e power minus j omega n, right?
Yes. So, simply because Z is equal to e to the power of minus,
No,
yeah, Z is
Z
equal to
is
e to the
equal
power
to
of
r
e to the,
e power j omega.
yes, yes. So, that is the definition. So, with that definition, I can see the relationship.
Yes, now if I substitute here, if r is equal to 1, then this reduces to this. Is it okay? That
Okay.
is
But
x of omega is
yeah,
equal
yeah.
to x of z when my r is equal to 1.
Yes. Maybe, madam, in some books notations, I see x of e to the power of j omega. What is that?
No
That
problem, it's just notation.
okay? We can use x of omega, x of e to the power of j omega.
Yes,
Anything we can.
whatever is fine with you. It's just a notation, no problem. So this is the
Okay.
relation, and another thing that you observe here is this r equal to 1. R equal to 1 actually indicates your unit circle.
Yes.
So this is your unit circle of radius 1, and if this unit circle is in ROC, if unit circle in ROC exists, then the Fourier transform exists. Does it make sense?
Yes.
Yes. If
So
it converges for r equal to 1, then it means that this x of omega converges, which means that the
o-
Fourier transform exists.
okay. So ROC must contain unit circle
Yes.
for existence of Fourier transform.
Yes.
Yes. Okay. Now let's get into the Laplace equivalent.
Oh, I'm sorry, we discussed discrete time case.
Sorry. Sorry. Oh, yeah, yeah. That's what confusing. Yeah, right, right. Discrete. This is discrete time
Yeah, I
because we say
mentioned continuous and we discussed discrete.
discrete time.
Yeah, and the next thing that is for continuous time case. And here the two relevant transforms are, the first one is your Laplace transform. So the first transform is Laplace, and the second one is your CTFT, that is continuous time Fourier transform. So if you look at the Laplace transform, that is for any signal xt, it is basically equal to, so I'll write it in this way, x of s is equal to integral from minus infinity to infinity xt into e power minus st dt, where this s is equal to sigma plus j omega. Okay, and this CTFT is equal to x of omega is equal to integral from minus infinity to infinity xt into e power minus j omega t dt. Right. Now,
Again, this notation, madam, this capital sigma, small sigma. I understand some people told me that for analog frequency we use capital sigma, right? That sigma.
yeah,
Uh, Here for CTFT we use capital sigma.
yeah, we can use capital omega. Actually,
Oh,
while discussing Laplace transform in the lectures, it was used as small omega, so I use
oh, oh,
small omega. But okay, fine, no problem.
okay.
This x of omega is equal to some like this. Now let me substitute it here. So I can write it as e power minus sigma t into e power minus j omega t. So if my sigma is equal to 0, I get x of omega. That is, this x of omega is equal to x of s when my s is equal to j omega or my sigma is equal to 0. Both are the same things. Now if I look at it in the z plane, s plane, so this is my sigma and this is my j omega axis. So my Fourier transform lies here, which means that in the region of convergence this j omega axis should lie. So if j omega axis is present in ROC, then the Fourier transform exists. Is it okay?
Okay, okay. So, yeah, so this is the correspondence.
Yes.
When you are thinking in terms of a continuous time case, that omega axis within ROC, when we are talking about a discrete time case, unit circle must be within.
Yes.
Yes. Okay, okay. And ROC is always dictated by poles, right?
ROC is dictated by poles. Yes, somewhat.
In case, in
It's not
case,
present. They are not present in your ROC. So yeah, somewhat they are related to your ROC, your
yeah,
poles.
yeah, yeah. So the process is first we find ROC by finding the poles and check within that ROC whether unit circle is there for discrete case, whether JW axis is there in continuous case.
Yes. Another thing to visualize this is okay. So let's take the Laplace transform case. I have two signals. This is xt is equal to e power minus 2t u of t, and other signal is x. Let's say this is x1 of t, and other signal is x2 of t, and this is e power 2t ut. Now this signal actually is something like this, and this signal is diverging, like it goes to infinity. So if I try to find Fourier transform of this signal, it is simple. Like I'll just do minus from 0 to infinity. That is x1 of omega is equal to from 0 to infinity e power minus 2t e power minus j omega t dt. And since this real part is less than this real part here is less than 0, that is it is minus 2t will be dictating the convergence of this integral. So this is basically going to converge. This is going to converge.
Okay, okay.
But now if I consider this is 0 to infinity e power 2t e power minus j omega t dt. Now this is 2t. So as the t tends to infinity, this will shoot up to infinity. So this is not going to converge. Now if I I look at its Laplace transform, then this x1 of s, we have seen this is equal to 1 upon s plus 2, and the ROC is real part of s greater than minus 2. And here x2 of s is equal to 1 upon s minus 2, and again the real part of s is greater than 2. So if we look at its region of convergence, it is something like this. Here I have a pole at minus 2, and the region of convergence is like this. Similarly, if I have this signal here, I have a pole at 2, it is like this, and my region of convergence is this side. Now in this region, this is my j omega axis, this is included in ROC, and now this is my j omega axis, this is not included in ROC. So if this is actually a decaying exponential. So many times if I have a decaying exponential, it will converge. Many times, not always. Many times.
Okay.
So
Okay.
generally, if I have a term like e power minus t, its zero is always going, its pole is always going to lie in this region, somewhere here.
Okay. 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 Uh, yes, I got some idea now. See, there's another thing. I don't know whether it is covered or not. DFT, discrete Fourier transform.
Yes.
Yeah. So you can explain that in also how it is related to DFT.
I think that will be better to discuss once I discuss DTFT in detail.
Ah. Okay. Okay, ma'am.
So once I discuss DTFT, actually when we sample DTFT in frequency domain, we get DFT.
Okay. When we sample
Yeah, okay, I'll
DT.
just give you a brief idea about it.
Okay. Okay. Okay.
But I'll discuss if it is covered in detail, then I'll discuss it in detail for sure.
Okay.
So basically, this is my DFT. This is actually for n running from minus infinity to infinity, x of n into e power minus j k omega n. So basically, if I have a discrete time signal now, this omega is actually restricted over a range of minus pi to pi, or rather if I specifically say it is restricted to a range of interval, or of interval of a range of 2 pi. So this 2 pi interval, when we discretize in n intervals, then this basically becomes 2 pi by n k, each indexed by k, and this k will be running n, sorry, and this k will be running from 0 1 and so on till n minus 1. So when we do that, at that point we get DFT. So this is actually indexed by xk equal to summation n running from minus infinity to infinity x of n, and this omega is now discretized, so it becomes e power minus jk. Here I won't be having a k, jk 2 pi by n into n. So this is my DFT. So is basically when you discretize this frequency domain, you get DFT.
Yeah. Okay. So here discretizing in the frequency domain means one one frequency 2 pi we are dividing into n samples. Okay. Okay. See, where I'm getting confused. Normally, we use the word discretization in the time domain. This is the first time I'm hearing discretization in the frequency domain.
Discretization is a term. It is a general term.
Yes.
So it's not a time domain specific term. It is a normal English word. It is.
Okay. So, in frequency domain, discretizing. So, what is the significance of minus pi to plus pi? You said the 2 pi range.
Actually, for
Uh,
a discrete time signal, this frequency range is limited to minus pi to pi.
okay.
Actually, when you
Okay.
sample it now, the frequency range gets restricted to minus pi to pi, and then it again starts to repeat.
Okay.
Yeah.
Okay. Okay. Okay, so it repeats. Okay, the same signal repeats after 2 pi 2 pi.
Yes, I'll discuss this in detail when we
Okay,
do DTFT.
okay, madam. So I'm
Yes,
just want to have conceptual high level views so that what is what.
this periodicity I'll discuss when we discuss DTFT for sure.
Okay, okay, madam.
Yeah,
Thank you.
okay. So this was all I wanted to cover today. So
Thank you, madam.
thank you.